summer program. The name suggests this is because the first crypto program that happened at Sinus was exactly 10 years ago. It was an amazing time, transformative for many young researchers and seniors alike. And I hope this program will be the same for most of you. And we have a few workshops in this program, as you all know. This is the first one, bootcamp, which is primarily meant as tutorial in the main themes of this program. So we'll have foundations, obfuscation, proofs, MPC, and many other relevant topics. There are several logistic things that I need to mention, but I'll mention them later because I myself do not know them right now. Once I find them out, I'll tell you. And sorry, I think I'm done. Oh, I'm done. Let me start the workshop, the bootcamp workshop, with the first speaker.
Right, the mic is working. Right. So good morning, everyone. I'm Iftach. I'd like to thank the organizers for inviting me. And just a quick poll before I start. Those of you who took crypto course, can you raise your hands? Any crypto course, just to make sure we're on the same page.
Maybe ask to raise your hand if you didn't take it.
No, this is insulting. And most theoretical crypto course, you know, one function-based cryptography, etc. Anyone took course that teaches that? Like the more basics, the fundamental. Okay, good. So most of you think didn't, which is great. Okay. So Yuval asked me to give this talk about foundations of cryptography. So I asked him, what should I speak about? So hi Yuval, he said he's going to watch. He told me, well, do the essential, like 10 minutes about really the basics, and then do whatever you like. So this is what I'm going to do. What I'm going to speak about? I'm going to speak about minicrypt. If you don't know what it is, never mind, I'm going to explain. But mostly about one function-based cryptography. Constructions, limitations, necessity, etc. This is going to be the first part of the talk. And also a bit beyond one function, don't be worried. And then I'm going to speak what most of you probably know as public word, or public cryptography, or cryptomania. I prefer to call it computational correlation for a reason I'm going to explain later. Okay, good. And a common theme, a common thread for this talk is going to be computational notion of entropy, which is, I think it's a beautiful concept, which says the following. You identify, say, in one function, some property, which is an analog of information theoretic property, in particular of some kind of entropy. And after doing that, if you do it with the right computational notion, you could use both information theoretic tools with this primitive, and more importantly even, you can use information theoretic intuition. Because, you know, we have from good intuition about information, or better intuition about information theoretic primitives than about computational ones. Again, you gain twice. Both you get the tools, not the proof, but the tools, and second, you get the intuition. Okay, this is going to be a common theme for the whole talks. Minicrypt. So, you know, as the joke goes, first God created the earth, and then the sky, and then one-way functions, right? I mean, at least this is where I grew up in Weizmann. This is what people thought. So what are one-way functions? One-way functions are easy to compute and how to invert functions. A bit more formally, you know, it's polynomial time computable functions from, say, from n bits to n bits. That's it's general enough. And for every probabilistic polynomial time algorithm, it does not invert it on a random output with more than negligible probability. What is negligible? You know, I'm not going to get into it. All of you know it's smaller than 1 over polynomial. Good. And this is the most unstructured primitive in cryptography because it basically assumes nothing. It just says function. Just give me any function, which is polynomial time computable. Otherwise, you cannot do anything with that, right? And it's how to invert. And it's also implied by most crypto. In almost any cryptographic primitive you can come up with, there's a hidden one function. Sometimes you have to work hard to find it, but eventually you do. And thirdly, much of crypto, not all of crypto, of course, but much of crypto can be based on the mere existence of one function. So from this unstructured primitive, you can get this whole set of applications, which is amazing. I mean, this is like, now it's taken for granted, but it wasn't like that in the beginning. And the way it happens is by intermediate primitive, set of intermediate primitive, is we take the one function, use it to get these primitives. And then from this primitive, it's much easier to get the applications. Good. And the most important intermediate primitive, I think, by consensus, is pseudo-random generator. Okay? So I guess you all know, but still, the pseudo-random generator introduced by Blamikali and Yao back in '82. This is a polynomial time function that stretches its input. Its output is longer than its input. Its output is computationally distinguishable from uniform. A polynomial time algorithm cannot distinguish from the output of this algorithm on a uniform input from a uniform string, even though they are very far apart, because this pseudo-random generator stretches its input, the statistical distance is at least 1/2. Okay, but still, a polynomial time algorithm cannot distinguish. Good. Okay, so we know what is on a function, what is pseudo-random generator. Now let's zoom out. What can you do with the one-way function? Okay, so the most important construction, because of the importance of pseudo-random generator, the most important construction is the construction of pseudo-random generator from one-way function. Okay, once you have that, there's a whole set of additional primitive you can construct directly from the pseudo-random generator. You don't have to use the one-way function any longer. You can work directly with pseudo-random generators, such as private key encryption, method authentication, pseudo-random function, and more. Okay? So most of the one function-based crypto is based actually not on one function, it's based on pseudo-random generator. There are a few exceptions, most notably universal one-way hash functions, or WOFs, if Evgeny would be in the audience. And these are used for digital signatures and identification schemes. And also statistical ID commitment, used from statistical zero. I'm a bit biased, okay? To be fair, you give a foundation, you give a talk, you're a bit biased towards your own talk, so towards your own taste, okay? So maybe the way I put it, Raphael would put something different here than statistical ID commitment, but I think it's important to put it here. And you get statistical zero knowledge argument, and then you get everlasting secrecy. And there are more, okay, which I'm going to ignore for this talk. Okay, so this is the one function-based crypto in one slide. And for the next few slides, I'm going to speak about this construction of pseudo-random generator from one function. And every request, I didn't prepare enough slides. I mean, I prepared more slides than Noam told me I have to reduce the number of slides, so I did. So you really have to take part, okay? Otherwise, unless you want to have a very long break in the second hour, okay? So please ask as many questions as you like. I'm not going to add slides, but to every whiteboard, I'll be very happy to answer any question that come to your mind, please ask, okay? I know it's the first talk of the school, and everyone is a bit, I don't know, shy is the right word, but still, please, yeah.
My question is, do we have any, like, what would be considered in pure mathematics a form of proof that one-way functions actually exist?
No, if P is equal to NP, there's no one function, right?
So we believe they exist, but we don't have a proof.
Yeah. We believe actually there's no proof, but we just believe, yeah.
So one-way functions imply all of these things in the second row.
Yes.
What are some primitives that one-way functions do not imply? That
We're going to discuss. Great question. One function is not sufficient for all of crypto, as you know, but we're going to discuss. More questions? Thanks. So one function is pseudo-random generator. Definitely the most influential and important reduction construction in this area, okay? Just look at the names. The first construction was from one-way permutation. It's a one-way function, which is also a permutation, whereby Blamikali Yao, back in '82. Then Goldar, Kravzik, and Luby in '89 constructed one-way function from unknown regular one-way function. It's a one-way function which is regular, even though we don't know the regularity. There is some regularity. And then Astad, Impeliazzo, Luby, and Levin made the final step constructing really pseudo-random generator from one-way function. Okay, and So the first construction of which made the full way was in 91, but still there are constantly many advances on the construction of pseudo-rank generator for one functions, improving the construction, simplifying it, etc. We're going to discuss it. And even today, Noam sitting there, and Rafael, and Noam, and Japan Jeng introduced new construction, improved construction for this in this area. Okay. Good. And not only that, along the way, these constructions came up with new conceptual contribution, such as, it's amazing, leftover Lash lemma was first proof in IL, in HAIL, randomness extractor. I don't think it was defined explicitly, but the leftover Lash lemma actually was the randomness extractor. Pseudoentropy, really one of the main contributions, even foundation-based cryptography used elsewhere, used a lot of complexity theory, right? Was in the very same paper, okay? And then more modern, next bit pseudoentropy, we want to discuss it, KL-hardness. All these concepts were introduced in the effort of doing one function-based pseudo-rank generator, okay? Good, so what we're going to do now, we're going to discuss some of this construction. We're going to start with this construction, the HILL, and then we're going to move to HRV. Okay. Okay. So how do you construct a pseudo-rank generator from one-way functions? I have a clock here, just to, yeah. Amazing. It's almost 10. I don't know what I did this time, probably someone else, but so how do you construct pseudo-rank generator from one-way function? Well, you do it slowly, okay? Because you start from one-way function which is unstructured, and you go to pseudo-rank generator which relatively has a lot of structure. So what is typical to this kind of construction for all of one-way function-based constructor? You cannot do it in one shot. You don't take one function, beat it out, and you get a pseudo-rank generator. What you do, you take something in between, which is this going to be one step for one function, but it's a very relaxed form of pseudo-rank generator. What kind of relaxed form? There's several options, but it's a very relaxed form of a pseudo-rank generator. And then you use information theoretic tools and intuition to purify it, to improve it till you get a pseudo-rank generator. But the important step is this first step, where you get this relaxed version of pseudo-rank generator. And the way the quality of this first step is defined is via the notion of a computational analog of entropy, which I'm going to introduce. Okay? So this was from iBird view, but this is the actual construction. So this is what we consider. Actually, I'm a bit cheating here. I want to say soon where. So you take the one function, okay? So what is this construction? G takes two input, x and h. X is just the inputted one function, okay? So we output it. And h is the n times n Boolean matrix. And for convenient, rather than say a times x modulo 2, I'm going to write h of x, okay? So it outputs f of x, it outputs the description of the hash function itself, of the Boolean matrix, and then it's not going to output h of x, but only the dx plus 1 bits of it, where d is log the degeneracy of f of x, namely log the number of siblings x has with respect to f. Okay, plus 1. The plus 1 is important. So again, what is this pseudo-entropy generator? It outputs f of x, it outputs h, just copy it from the input, and then it outputs some bits of h of x. Not all of it, some. How many? Depends on x. And so the output of this generator are going to change according to x. If f is regular, then the output is going to be the same length. But if f is not regular, the output length of G is going to be different. So the definition is clear. There's one issue with this construction, which is?
Is it efficient?
Inefficient. Right. Why is it inefficient? Because this function, d of x, the degeneracy of x, is, we assume it's hard to compute. what we believe about the world is how to compute. Actually, if it was easy to compute, there are much simpler construction of pseudo-random generator for one function. But we have no reason, absolutely no reason to believe that it's easy to. But let's avoid it. I'm going to handle it later on, but let's ignore it for now. Okay, let's ignore it, assume it was efficiently computable. Still, there's much things to say, even if it's efficiently computable. So my first claim is that this function, if you remove the last bit, is injective. Okay? Namely, it's not really injective, but it's close to being injective. Almost injective. In what sense? That a typical output going to have only a single preimage. Why is that? So essentially, H, a Boolean matrix, is a pairwise independent hash function, and therefore it should have this effect. The only proof I have that came to mind, I think there's a direct proof, use collision probability. You can prove that the collision probability of this function is very high, and therefore it cannot be that many of the output has more than one preimage. Okay, but intuitively it should be clear. Nothing very interesting. You know, there's two dx inputs going to the same image. I output dx bits. They should kill all the degeneracy. Okay, to make it one-to-one. Intuitively, it should be clear, and there's a simple proof which is going to skip you.
When you say almost, you mean kind of randomly over H?
Randomly over H and X. Yeah. It actually suffices to do randomly over H. Okay, good. Thanks. So everything when I say almost injective, a good point, is over random X and random H. Or I'm going to say I care about random X and random H. Good. More interestingly, I'm going to ask what is the entropy of the output of G prime? Again, G prime is G without the last bit over a uniform input. So what is entropy? Entropy is the Shannon entropy, okay? And Shannon entropy of X is given by this formula, is the expected log 1 over the probability. If you never heard about entropy or never see the formula, just ignore this line. Just remain with me on the intuitive level, okay? So intuitively, entropy is a generalization of uniformity. So rather than asking, like, it asks how many uniform bits are hidden in X, okay? Or what is the unpredictability of X? If X is thus uniform string, this is thus the length of the string. But more interestingly, where X is not uniform distribution, okay, for instance, over some domain, and still you can ask what is the unpredictability of X, okay? Many different interpretations of what entropy is, also the description f of X, etc. But I think for this slide, at least, let's keep with the unpredictability of X, okay? How hard is it to tell what X is going to be without knowing nothing, okay? Good. So I claim that the entropy of G prime is just the input length. And why is that? It's true for any injective, assuming it's really injective, it's true for any injective function, because it follows immediately the formula, but basically you transform all the entropy of the input to the output, okay? The output is just uniform over the range of the function, okay? And the range is exactly this, the length of the input domain, and therefore you get that the entropy of the output is just the entropy of the input, which in our case is just the length of the input, which is X plus AH. Till now, it's not very interesting. Okay, we take a function, we convert it to injective function, and now we said that the output entropy is just the input entropy. Well, not very exciting. It's getting more interesting now. What is the entropy of the last bit? Again, I already extracted all the entropy of the input. So what is the entropy of the last bit?
Given what?
Given the rest of the input. Given that, this part, what is the entropy of the last bit? 0. Why is it 0? Because entropy is not coming off the thin air. Okay, you can never, by applying deterministic function, the entropy never increases. Okay, and more importantly, it's just any. There's 1,000 proofs. Okay, the input is already determined here. So if this is determined, what is the predictability of the next bit, which is determined? So the unpredictability of a fixed variable is 0. It's as predictable as it can be. Okay, good. So there's no entropy here. But I claim that G prime is one-way function. And why is it one way? Anyone can tell me why is it one way? So F was one way, right? H itself, is independent of F, so definitely it's not help you to invert F. But why these bits are not useful for inverting F? Maybe after you see these bits, H of X till 1 till D of X, you suddenly are able to invert F. Yeah.
H is random.
H is random, yes. But H of X is a function of X. So it gives you information about X.
No, because H is random, should it not?
Again?
Because H is a random matrix, shouldn't H of X sort of be distributed independent of X?
Why?
Intuition.
Intuition is true, but why?
No, it's true if you don't know H, but if you're
You
given
know H, it appears in the clear. If you didn't know H, so clearly.
Yeah.
Okay, that's the entropy of H itself, but H put in the output. Leftover lemma. Exactly. This is what the leftover lemma says. It says the following. There's dx degeneracy bit in X given f of X. The entropy of X given f of X is exactly dx. And the leftover lemma says, well, you can extract this number of bits. Okay? Basically, a random pairwise independent hash function or a random Boolean matrix in this case is a good extractor. So actually, I'm slightly cheating. As put is not correct. There's something called entropy loss. Only, say, this bit till here, when you remove log n, are very close to being random, and this bit maybe not. But again, morally, this is what happened. I want to ignore this subtlety. Good. So why G prime is one function, F is one function, H is random, and these look uniform. If you look uniform, assume you can invert it, then you can invert also F itself. Given X, you would sample H by yourself, and sample this part uniformly at random by yourself, and you can invert it. Okay, random inputs who are independent of the input are not useful to invert one function. Good. So G prime is one function. So, sorry, there's something missing here. There was a call out now. This, what is the last bit? It's just the Goldach-Levin outcore bit. Why is that? Think about it. What is just the dx plus 1 row of H. This is H. This is the dx plus 1 row of X. Inner product with X. This is what this bit is. So this construction, which is H dx plus 1, inner product in X, is what's called the Goldach-Levin outcore predicate. And what do we know about this predicate is that if G prime is a one function, the output of this predicate is indistinguishable from uniform. So while information theoretically, this predicate, this bit is determined, it has no entropy whatsoever, computationally, it's look uniform even after you see all this part. Okay? And this is nice because we use H for two reasons. The first part of H, we use it as a pairwise independent hash function for the leftover last lemma. This row of H uses as the outcore predicate of the random vector for the outcore predicate of Goldach-Levin. Good. So this looks uniform. So I claim that all in all, the output of G, now not G prime, but G as the input length, which is n plus h, plus 1, this one is coming from the last bit, pseudoentropy. What is pseudoentropy? Pseudoentropy is the first computational analog of entropy we're going to introduce today, which says the following. It's the most basic one. It says X as pseudoentropy K if exists a random variable Y, which is really as entropy is really K, and still is computation indistinguishable from X. So again, X as pseudoentropy K if it's effectively as if it has K bits of entropy. Effectively means there's different random variable, which you cannot distinguish, which really has k bit of entropy.
But okay, you generated only one bit of
Pseudoentropy,
randomness.
yeah.
But you lied because you can't really apply the leftover hash lemma on so many bits.
I'm applying it on single bit.
No, the leftover hash lemma.
I apply the leftover, like can apply it, random as extractor, can apply it on.
But you can't apply all the way.
Yeah.
So you.
Yeah, so what you do in practice, I cheated, right? Let me finish it and then I address where I cheated. Okay, you are right. I said that I was cheating and I'm going to address. Let me finish this argument. I'm going to. Okay. So I claim that the output of G of a random input is indeed this amount of entropy, pseudo-entropy, according to this definition. What Y I'm going to use for it? What random variable going to realize this pseudo-entropy of the output of G? How are we going to define Y?
Change the last bit to random.
Exactly, but it's not fair. Sorry, the student. So you change the last bit to random. So Y is exactly defined like G on random input, but the last bit you change to uniform bit. Why Y is indistinguishable from the output of G? This is what we said before. Even though his last bit is uniform, we said that the last bit is computation distinguishable from uniform. And what is the entropy of Y? By definition, Y is the same entropy as before, and here we put a uniform bit, so clearly we add the entropy by 1. Okay? So the pseudo-entropy of this construction is greater by 1. And this is where the miracle happens. When we have this like a gap between the entropy and the pseudo-entropy, from here is more or less engineering. You know, you have to use some known tools. The proof might be subtle, more subtle, less subtle, but it's more or less engineering. Okay, the trick, the magic happens here. Question about what I said till now, because I'm going to modify it and show that actually it's not going to work, etc., etc. But so 2 questions. First, D is I know it's disappeared to me. This D might be inefficient, so we cannot use actual this construction. Next line, I'm going to say what to do in this case. And second, what Yael asked, say, well, actually, you've been cheating when using the leftover lemma here, because it's not true that all of it is uniform, close to uniform, because you cannot extract all the entropy. There's something called entropy loss. So what you do in practice, it is true when you remove log n bits, say, and the last bits, you enumerate over all possible values. You just enumerate in the construction. You say you think about all the bit till now really look uniform, and the last bit is just enumerate over all possible values. So assume there was an algorithm that could invert if you're getting this value. I will use it by sampling this part uniform and enumerate over all possible value for the last log n. This is what you would do. Okay, but I didn't want to get into it. Okay, good. It's a good time for a break. I can take, because I'm speaking like 20 minutes, I think. So 30 minutes. What do you think?
No, we have an hour.
Yeah,
We're an hour. When did I start? Ah.
right there, yeah, you have time.
So fuck, yeah, so yeah, good, good. Yes, right. Good. So you cannot use this construction because D is not computable efficiently. So what do you do? Is there AC here that is off? Right?
Working too hard.
Yeah. No, that's hot. Yeah. Anyhow, so what do you do? So rather than using this construction, which is efficient, we use the following construction. Namely, G get an additional input, which it uses it to decide how many bits of H of E is going to output. It's part of the input, and it's actually also part of the output. So it should be I here. Okay, I appears also the output. So
I is random?
I is random. I is random between Y and N. Okay? So what I'm claiming is this, well, this construction is efficient now, right? By definition. And Y is not as good as the previous one, is still an entropy gap. It is not 1 like before. The entropy gap is between the pseudo entropy and the real entropy, but it's 1 over N. Why is it 1 over N? Because I is the correct value of dx plus 1 probability 1 over N. And in this case, you get 1 bit gap. If you overshoot, if you overshoot by I, namely, you see it? No. So this is dx plus 1. If I is here, you are very happy because you get exactly in the previous situation. If I is larger, then what goes wrong? If I is larger, if I appear here, what goes wrong? Why cannot just simply set I to n? What goes wrong with the previous construction if I is too large? G prime is not one way. You gave me too much information about x. It's not close to uniform. And therefore, assume you output all of it, you're given h of x and bits of h of x. Clearly, it's very easy to invert. Let's apply the inverse of h, you get x back. So you're not getting pseudo-entropy, but what you get the entropy, which is fine. Okay? If I is smaller, it's slightly more complicated. Now, definitely you don't get pseudo-entropy because you didn't even output all the entropy. But still, you get the entropy of the output. So all in all, probability 1 over n, you get the bonus, the 1-bit gap. Otherwise, nothing good happened, but nothing bad happened. So you get gap 1 over n between the pseudo-entropy and the entropy. And it's enough. It's enough to construct pseudo-random generator. Okay? Still, it has this construction.
Wait, sorry, but if I is small, it's not, you lost.
You output, good, very good point. You didn't output, there's a gap between the entropy of the output.
And
Both of them might be smaller than the entropy of the input,
exactly.
which is fine. It's fine. It's still fine. No one said it's not as good a pseudo-entropy generator, but it's fine. They call it the original paper false pseudo-entropy generator. Okay? But it's fine. Okay? But indeed, this is the second point. So pseudo-entropy gap is small. That's 1 over n. And as Yael said, the output pseudo-entropy might be smaller even than the input entropy. Actually, this is the typical situation. But still, as long as there's the gap between the pseudo-entropy to the real entropy of the output, you're fine. Don't ask me why. It's a complicated construction. How you do that? I'm not going to go into it because we're going to have a much better construction. And not only that, the value of the pseudo-entropy is unknown. It's a function of f. So these three disadvantages translate still, but before that, using information theoretic tools, you can get a PRG. Still, this gap suffices to get a PRG, but not very efficient. Specifically, you make n to the 8 number of f calls, and the seed length for the pseudo-random generator is n to the 8, assuming that the one function you started with was n, which is rather poor. Good. So this was Hill. Okay, this is the Hill construction. Yes.
So I get inefficient, but I thought it was just you repeat in parallel and hash.
No, it's more complicated because you don't know the entropy gap. You have to do combiners. You have to work out. It's not just doing parallel in hash. You don't know how many bits to extract from the input. There's many, many complications. Good. So this was the Hill. But remember, consider this hash function, and the problem in the first construction, because we didn't know where to truncate. It wasn't computational efficiently to decide where to truncate. So they truncate at random, and this was bad. What happens if we don't truncate? Right? Should be a funny joke, this pot with a curly hair. So no one laughed. Anyhow, ChatGPT took me like 3 hours with ChatGPT to draw it. Namely, if you consider this function, this generator, f of x, h, and all of h of x. Stupid, right? It's not even a one function. Right? Why it's not a one function? Again, the inverse of h, you can compute the inverse of the h, let's find out x. So G is invertible, thus has no pseudo-entropy gap. I mean, there seems there's no crypto. But it turned out there is. Why? Because if you look at all the output of G, you manage to invert it and then everything disappears. But if you go from left to right, at this point, which is exactly after output dx bit, this is exactly where we were before. This bit is going to look pseudo-random. It is true that when you get here, you found out that you've been cheated. It actually was determined, but this is too late for you. With the right notion of pseudoentropy, you have entropy gap. And again, this subtle, most subtle pseudoentropy notion suffices to construct pseudorandom generator. Okay, this one I'm going to define. I'm going to formally define what this notion of pseudoentropy is. So this is what's called next block pseudoentropy in joint work with Omer and Salil 15 years ago. So those of you familiar a bit with entropy know the following. The entropy for random variable, x, if its k-bit is equal to the sum of its conditional probability. It's equal to the sum of the entropy of the first bit plus the entropy of the second bit given the first bit plus the entropy of the third bit given the first bit, etc. It's called chain rule. Okay, and conditional entropy is this formula. It's just the expectation over the entropy of x, and the expectation is over the condition. Okay, this is no faculty entropy. This is chain rule for entropy. If you walk by parts, you lose nothing, you gain nothing. You get exactly the entropy. But I want to look at it differently. I said, what it means? It means that if you look at x, it has next block entropy. I mean, it's rather hard if you go bit by bit or block by block, depending on the source. It's rather hard to predict the next bit given the previous one. How hard? K hard. Okay, this is exactly what this means. Because this is a lot of entropy, it means given that this is not determined, definitely it's hard to predict it. So we can view entropy. It's equivalent to the original definition of entropy. Say random variable is x bit of entropy if it's k hard in this sense to predict the bits in an online fashion one by one. Every time you know the history, you have to predict the next. Okay? Good. Till now, nothing. It's like tautologies. Okay? Said nothing interesting. Here is the interesting part. We define that x as next bit pseudoentropy, or next block pseudoentropy, if these bits are not blocks, if the following happen. There exists a random variable y, which again has n bits, say, such that given the prefix, the I, you cannot distinguish between xi and yi. Again, every part for every I, given the xi, x1 till I minus 1, you cannot tell xi by yi. And yi, if you sum the entropy of the yi given xi, it's at least k. So it means that the unpredictability of x is at least k. The computational unpredictability of x is at least k. Okay, because of y, it was by definition, the unpredictability of y given the prefix of x was at least k, and yi is computation distinguished from xi given the history. Okay?
For all I, right?
For all I. Good? So xi is somewhat hard to predict given the previous values x. How hard? K hard in the following notion. Okay? So let me tell you some interesting facts about this definition. First, those of you who know Yao unpredictability. So Yao, back in the 80s, said, well, gave an equivalent definition of pseudo-randomness, said a source is pseudo-random if you cannot predict it in an online manner, totally. Given that you cannot, every time you see the past, you know nothing about the next bit. It looks random to you. This is like more quantitative in the sense that maybe some bits of x are fully predictable. Maybe actually the first bit of x are fixed, and the third bit of x is exactly like the fourth bit of x. But still, all in all, it is k unpredictable. So this is a quantitative variant of Yao unpredictability, which wasn't that interesting notion for its own because it's equivalent to pseudo-randomness. But this is not equivalent to pseudo-randomness, and actually, it's not even equal to pseudo-entropy. It might be larger than pseudo-entropy. Well, this is like quite amazing. Why is that? Because we take a notion for entropy, these two notions are exactly the same. By chain rule, if you sum this entropy here, the parts of entropy is exactly equal to k. But with pseudo-entropy, when you move to computational world, they depart. One notion is smaller than the other one. And actually, it happens again and again, at least twice. And I'm not going to do it, but There's up and down. So you have a choice. When you move to computation analog of entropy, you have a choice. There's not only one definition. You have to find out the right definition would give you the bigger gap, and hopefully you're going to be able to work with it. Okay? So let me recap again, because it's an important definition. I pointed out that we started with an equivalent definition of entropy, which is just equivalent. There's nothing interesting happening here. But when we claim, and we're going to see it next slide, that when you move to its computational analog, it's different from the computational analog of entropy, of the original definition of entropy. Okay? Questions? Okay, so let me just finish this part and argue that the next block pseudo-entropy of G is indeed n plus h plus 1 larger by the entropy, like in the ideal incorrect construction we gave in the first slide. And this is the definition of pseudo-entropy, a next block pseudo-entropy. And why is that? Again, we know, I'm repeating what I said before, these bits are just, I extracted all the entropy from the input. And this bit look uniform on an observer. So what y is going to be? Where? What is the y that realizes the next block pseudo-entropy of G?
Just the uniform bit.
The uniform bit, exactly, almost exactly the same definition. Again, you take y, that's the bit of the output of G. When you replace, like before, the I plus D x plus 1 bit with uniform bit. But that's a word of caution. Y now is computation, it's jointly distributed with the x. It's important for this definition. Otherwise, there's no way you can get that. Okay? So in the pseudo-entropy definition, y was independent, it's just a distribution. Here, it's important that y is actually computationally jointly distributed with the output of G. Okay? And this leads, I'm not going to get into it. It leads to significantly more efficient PRG, seed length and number of F-calls on n cube compared to n to the 8. Okay? And using it, you have to respect again, when you manipulate computation analog of entropy, you cannot do whatever you like. You like, in a sense, to respect the computation analog of entropy you're working with, but still with the right construction it goes for.
So basically what you're saying is I'm first going to generate pseudo-entropy according to some definition,
Yes.
the original or the next block, and then there's a way to go from
Sometimes.
pseudo-entropy to PRG.
Sometimes.
Okay, are you going to talk about this part?
No,
Okay.
no.
So, but in general, is there kind of a generic theorem that says I can go from next block pseudo-entropy to a PRG?
No. You can come up, I guess, with some totally stupid analogs.
Yeah,
yes.
yeah. So, right. So
So the way you have to come up, actually, you do it in reverse, right? You understand what kind of construction you can do, and you never start in some sense with computation. It's the way to prove it, but you start some intuition and what construction can go through, and then you find a dark notion you can work with. Okay?
Okay, so this is really, you can't like take this notion and kind of purify, like say, okay, any string that has of not contrived according to the definition that has this next block pseudo-entropy can be converted to a PRG. You don't have anything.
No, but we do have a lot of examples, and actually I'm going to show to you examples of computational notion of entropy, which is totally useless. Okay, I'm going to see it soon. Okay? Yes.
I'm confused. Didn't Hill show that false entropy generators
Right, suffices.
implies, right?
Right.
It answers
Yeah, no, false entropy is only fine, but you ask something different. And you can come up tomorrow with the next different notion of pseudo-entropy.
It's just, is there a notion of entropy, like false entropy or pseudo-entropy or next bit?
Yeah.
All of those, if you have.
All of these imply PRG.
Yeah.
But you ask if I come up with the arbitrary
No.
notion.
I'm saying if you have, if I guarantee here's a string that has next block pseudo-entropy.
Yeah.
Can you take that on its own?
And which is larger than entropy. And can you get it? Yeah, if this was the question, you can get this generically, yes, the same construction basically. don't care. It means that this string, if it generated efficiently, is thus a pseudo and next bit pseudo-entropy generator.
Yeah, but can you get from that a complete PRG?
Yeah. We're going to get from that. I'm not going to do it. From that, to get a complete PRG.
Yeah, but you're not going to show how.
Not going to show. It's less interesting. Sorry. Yes, but yeah.
I know you don't want to get into the details, but at some level.
At some level. So some level is the following. Okay, at some level, because I have time now, I thought I have 20 minutes more than I thought. So what is the high-level intuition? Well, this bit looks pseudo-random when you're at this point, but then when you see this part, it disappears. So what you do, you take many instances of that, shifted, and basically you think that you would XOR them. So you take extract of them. You're never going to see this bit. This bit going to be masked by other execution of the next bit pseudo-entropy, which is going to have real entropy here. So every time in every column, there's going to be enough, but you do some kind of entropy equalization. In every column, there's going to be enough entropy such that the bits that would kill these bits are masked by the real entropy of the other rows. They're never going to be exposed. The construction hides these bits, and therefore it never disappears. Okay? Sorry, be too vague, but yeah.
Can you explain what question you thought Yael was asking when you?
Yeah. I thought I'll ask if any notion of next bit pseudo-entropy is useful, and actually you're going to sorry, Yael, I didn't do it. No, sorry.
Yeah, that's fine.
Sorry. So I should have understood it, but I didn't. So I thought, and actually we're going to see example of a notion, very natural notion of pseudo-entropy, which, as far as we know, is not useful. Okay. Good. Great. Two more things. So first, actually, Salil and Colin took it a step further, so that you don't need H at all. F of x already has next bit pseudo-entropy n+1. Okay, the most basic construction one can think of. F of x is the right construction. Beautiful proof, highly non-trivial, way more complicated than the proof of this part. But still, if you want to see really a beautiful germ of this area. Okay. Secondly, Raphael and Noam took it a different way. Said, well, we want to stick with this construction. We're going to give a simpler definition of next bit pseudo-entropy, which roughly only cares about the case that the yi's are either constant or a full entropy. You call it, don't remember the name.
Bits unpredictability.
Again?
Bits unpredictability.
Bit sampling?
Bit unpredictability.
Bit unpredictability. Okay, so it is simpler definition and leads to somewhat slightly log n, I don't know, more efficient construction. But again, it's like the same construction and simplification, very nice. It's useful to think of the implication that suffices to construct the Doran generator. Good. So what we've seen till now, we've seen two notions of computational notion of entropy, pseudo-entropy, and next block pseudo-entropy. Both are implied by 1F functions. And it's easy to see that entropy implies next block pseudo-entropy, and the other way, it's not true. Actually, we've seen it. There's a source that has more next bit pseudo-entropy than entropy. But actually, these two are not the first computational analog of entropy that we consider. Yao, who else but Yao, considered a different notion of computational analog of entropy in early 80s. So for entropy, we know another equivalent form of entropy is the average length of the best compression scheme for X. So compression scheme is compress and then decompress. So the average length of the best compression scheme is, again, the entropy. In entropy, everything is the same. So Yao came up with a very natural definition. What is the best compressibility, which the compression and decompression should be done efficiently? Okay, very natural. He took another analog of entropy. Actually, he was the first one to do it, way before pseudo-entropy was introduced. And thus, if you only care for computational compression, what is then if it's k incompressible, if it cannot be efficiently compressed, the less than kb. Okay, it's a very natural analog of computational analog of entropy. And as far as we know, it's totally useless. What we do know, but it stayed there, and Yao says so many beautiful things came from Yao. So many people thought it's going to be useful. So first, it's easy to see that pseudoentropy, if a source has k-bit pseudoentropy, it also has k-bit incompressibility. Other direction was not known, and then we proved the oracle separation between the two. It's also easy to see the next bit pseudoentropy does not imply incompressibility. Actually, if you think about fx, fx and x is very easy to compress it. How do you compress this source? X. Right, you just write x, but it has next bit pseudoentropy. So next bit pseudoentropy does not imply Yao incompressibility. And we know in JAD, we proved that the other way around. We saw that actually source has k bit of incompressibility. It has k minus 2 bit of next bit pseudoentropy. So Yao incompressibility is essentially between pseudoentropy and next bit pseudoentropy. So it is between two useful notions, but for its own, we don't know anything useful of it. So there might be, I mean, but we don't know. There's also a different notion called inaccessible entropy, which implies statistical ID commitment. Again, another construction you can do from one function. And interestingly, there, the inaccessible entropy is actually smaller than the real entropy. Previously, all notions were larger than the entropy. There, it's smaller than real entropy. And something which is nice is that the construction is essentially the same construction. F of x and x achieve this gap between accessible entropy and real entropy. And finally, if it's written there, Agrawal, Chen, O'Reilly, and Vadan gave another notion of pseudoentropy called KL hardness and proved that it implies box, it basically unify both next block pseudoentropy in inaccessible entropy. Okay, so this is what I want to say about, I think it's a good time to make a break. If it's fine to make a break a few minutes before, because it's a good time. So yeah, let's take the break and then continue. Thank you. היי, מה המצב?
בסדר, מה נשמע?
מה קורה? יופי.
זה שנים. אז אתה פה?
סוף.